Hi, today I would like to use a curve called parametric curve called Lissajous curve in order to create some geometrical sculptures in Houdini. This is going to be pretty simple to implement. You might learn something new. So this is the Lissajous curve drawn in Houdini, and there are some parameters you can control in order to change the shape of it, like these. And the curve itself is pretty easy to implement. You just need to use some equations. You just need to implement some equations for x, y, and z. So that itself is not that interesting for me. So I wanted to use this base curve in order to create some interesting sculptures. So as a result, I made something like this, which you have a pipe through a base curve, and you also have some bone-like structures attached on top of the curve like this, and with the animation rotating using a curve as an axis, rotation axis, like this. And let me make it a little bit row red so that I can animate in real time. So this is kind of things that I want to create here. I have set some parameters you can control in order to create a bunch of bone patterns on top of this research curve, like the length of the bones, how twisted the bone is, like this, and the speed of the rotation, and so on. So let me get to it. Let's create this kind of geometry using a research curve. So if you go to the Wikipedia, you can kind of check out the equation how to create this kind of curve, and which is written like here. In this case, the curve equation is only explained in 2D, but you can actually add third dimension, or if you want, you can also add fourth dimension, but I am going to do with the 3D. And as a result, for X, Y, and Z, you can express each of the coordinate X, Y, and Z like this. So A is the size of the wave, determines how big it is in X, Y, and Z direction. And using sine as a base parameter, basic parametric curve. Mx is a integer value in order to determine how many rotation you want, combined with 2 pi, which is correspond to 360 degrees. T is a value that you use for time value, which goes from 0 to 1. So you can also write like delta t. So you make a for loop to iterate from 0 to 1 in order to calculate this value, so that you have a closed loop curve. And finally, you have some offset angle in order to control the final shape. And you do the same for y and z with its corresponding parameters. Now t is always the same for x, y, and z. Only the a, m, and theta is different for x, y, and z to control the different kind of shapes. So keep that in mind. Let's start by creating those research curve using those parametric equations. So let's create a geometry node, and I will start by creating a attribute wrangle, set in as a detail, and create the base point for this parametric curve called Lissajous. A first parameter that I want to have is number of points. So I'm gonna just set it as number, and let's have some parameters like mx, my, mz, ax, ay, az, theta x, theta y, theta z. Right, so I'm gonna ax, and I am going to parameterize every parameter here. I'm gonna promote it as a channel for every parameter that I can control, that I want to control in order to change the shape. Okay, now I have those parameters. Let's have all those parameters transferred into a null node, which then I can control it later on by accessing to this null node. I'm gonna color this as a blue. Open up this edit parameter interface. Then I'm going to uncheck this 4-bit linking parameters from outside the subnet. Go back to the wrangle. Then I'm going to drag each of the parameters into a parameter interface, starting from the number, then ax, ay, az, mx, my, mz, theta x, theta y, and theta z. And I'm also going to set some ranges for the number of points. I'm gonna set it to the maximum, something like 300. For ax, ay, and az, I'm gonna set the maximum to 5. mx, my, mz, I'm gonna set the range from 0 to 10, that's fine. And for theta x, y, and z, I'm gonna set to 0, 1, and that's also fine. Right, now if I change those parameters, all the parameters should be linked to this wrangle. Okay, looks good. Alright, next thing, I'm going to actually write an equation in order to actually draw the curve. So let's go back to the code editor. Let's open up the editor like this. And then, starting from a for loop, I'm going to add a point at each delta t position, delta t value, which the delta t is from 0 to 1. With the maximum number of the num that I have just set it as a parameter. Okay, first of all, let's create a value called t, which should be from 0 to 1 within this loop. So I can divide I with number minus 1.0, which should be in the range between 0 to 1. Then I'm going to calculate the x, y, and z coordinate based on this equation. So let's keep this on the right here, and x is equal to ax multiplied by sine and mx multiplied by 2 by pi times t plus theta x. Right. So y and z is pretty much the same. You just copy this 2 times, replace x with y and z. Okay, now that I have those coordinates, let's make a point in this xyz coordinate. So using add point function. Like this. Okay, now it sees kind of a point scattered inside the space. Yeah, I think it is showing some kind of pattern here. Now let's also set an attribute to this point that I have just created with the value t here, which I could use it later on for kind of advanced geometrical expression. So set point attrib, I'm just gonna name it t, and then pt t. Okay, this. Now exit the code editor. I think it looks good enough. Currently it's just a point, so let's create a curve from those points using a add at node. Connect with the add node and set it to polygon by group, and you have this connected curve which already looks like a Lissajous curve you saw on Wikipedia. And if you change those parameters you have set, like the size of A, you're just changing the x coordinate size, y coordinate size for A value, z coordinate value. mx, my, and z is controlling the loopness of the x coordinate, y coordinate, and z coordinate, which changes how it loops within those coordinates. And combining those three m parameters makes some interesting patterns, and sometimes it gets flat like this. Okay, looks good. I guess I like this pattern. And theta x, theta y, and theta z is the offset value, which is which currently isn't used as a angle. I mean, this is used as an angle, but the range is between 0 to 1, so let's multiply this theta by pi multiplied by 2, so that if the value is 0, then the angle is 0. If the value is 1, then the value will be pi multiplied by 2, which corresponds to 360 degrees. Let's just copy this. Okay. Right, that looks good. Again, most of the time, the parameters you want to change is those m value and a value. The t value wouldn't change much of the shape. So the Lissajous curve itself is pretty easy to implement, but that is not that interesting as it is, so I'm going to create some geometrical sculpture on top of this curve using the information that I've just created. What I want to do first is to split this curve using the intersected point. So separate those curves using the intersected inner self-intersected point. Then separate each curve and create a bone-like structures on top of it, except at the end point, which corresponds to the intersected point of this whole curve. Because I don't want to create like duplicate bone structures on same point. So in order to do that, in order to split those curves using the using the self-intersected point, what I could do is to first find out the intersected point, where the intersection, find out the intersection point using intersection analysis. Now connecting this curve into the first input of the intersection analysis, it automatically finds out a self-intersection points, so that's good. So in order to get the splitted curve, what you need is the u value of the curve for the starting point of the splitted curve and the u value of the end point of the splitted curve. So to get that, what you want to have is this prim uv w parameters from this intersection analysis node. By checking this primitive UVW for each point, for each intersected point, you should be able to find out where is the intersected point written as UV. And since this is a curve, only the U value is written as a intersected point address position. So what I'm gonna do next is to just pick the first value for each source primitive UV at each point. Then I'm gonna add it inside the float array, then sort it out based on the value, then use it in order to split the curve. So I'm going to create another detail attribute, wrangle, by creating an attribute wrangle first and set the ran over parameter to detail, then connect this intersected analysis to the first input, and then this curve itself, the curve value itself, to the second input. And I am going to name this as UV pairs to store all the UV pairs in order to create a separated curve value. Okay, let's write some code here. Now, first thing I would like to do is to create an empty float array to store all the U value that you have found using this intersection analysis, which corresponds to this. So some points have like multiple UV values. Some points have only one value, so you want to look at all the information. Some of the value are duplicated, but we'll just ignore about that. So float US equal to empty array. I'm gonna create a position array as well. Maybe not. Maybe I don't need the position. Okay, I'm just gonna create a U value here. Float array for storing the UV's U value, and kind of iterate through all the points, all the intersected points using for loop. And first of all, get the prim UV's attribute from the point like this. And then since this is also a float, I'm gonna create this is also an array of vectors. I'm going to create another for loop like this, and access to each of the UVs. Okay, now the value that I want is the first value of this UV. So I'm going to push this U value from UV into a US float array here. I'm going to create a vector2 UV pairs array to have the first point U value and the end point U value for each segmented curve. So to do that, first of all, I need to sort this U value based on its. I need to sort this US float array based on its stored values. So I'm just going to do that using sort function like this. Simple enough. Okay, now for the UV pairs, first I'm going to create a empty array, then loop through all the U value within this array, sorted array. Okay, and float U1. I'm gonna get the first U value from the sort, and then I'm also going to get the next U value named as U2 using I plus 1. So the reason why I loop through the length of the U value, U array -1, is because I have this U I plus 1 here, right, in order to make the pairs. So let's make a pair U pair with the vector2 value. Vector2 U pair set U1 U2, and then push this value inside the UV pairs that I have created as an array. Maybe I should just say U pairs. Okay. That should work. Now sometimes if the curve is flat, the intersected point the number of intersection point becomes really vastly bigger than should be. Like for example, if the mx is one like this, and you have a curve like this, and you can see that there are duplicated curve like here, which creates a vast number of intersections. Now that is not what I want, because if you just use all those intersection point as a segmented point, then each curved length will be really small, really short. So to avoid that, if you have the number of intersected points, currently like 246, is bigger than the original curve points like 186, then in that case I'm going to just create a UV which is from 0 to 1, and that's all. If not, if the number of intersected point is less than the original curve point number, so if the original curve's point number is 186 and the intersection point number is this is still intersected. I should change the m value, something like this. Yeah. So in this case, the intersection value is less than the original curve point number. So in that case, I'll just gonna use the value that I have created here. But if not, if the intersection point number is greater than this point number, then I'm just gonna create one pair, which is from 0 to 1. So to use that condition, I'm going to calculate the number of points from the first input, then the number of points on the second input. So if the number of the points from the first input is less than the second input, then I'm going to create an attribute called pairs using the pairs vector to array that I've created here. And I'm also going to create a pair count showing how many pairs you have. Like this. If not, if you have too many intersection points, then for the pairs attributes, I'm going to create a array with just one vector 2, which have from 0 to 1 as a u value. And obviously the number of pair count for this one is 1. Okay. And if you look at the detail attribute, I should be able to see some value here. So in this case, if the intersection number of points, intersection points number is less than this curve point number, then you have a pair count more than 1 with a UV value which defines as a segmented u value. So from 0 to 0.02 is the first segment, from 0.02 to 0.1 is the second segment, so on. Now if you change the curve to the more flattened one, something like this, where you have tons of intersection points, then as a result you only have one pair count, which is created with a u value from 0 to 1. Okay, now that seems to work fine. Now I'm going to access those detail attribute later on from for each loop, so I'm going to create a null node named with a capital letter so that I can access it later easily. Right, let's change this value so that the curve will be more interesting. Okay, something like this. Yeah, this looks good. Alright, now let's then create a for loop in order to create a bone structure on top of this curve using this segmented curve information. Okay, gonna bring this up to the left side. And first thing I would like to do, in order to create a bone structure, the rotational bone structure, I need some information on top of this curve, which is the frame orientation, the normal direction and the up direction for each point on this curve without much of a twist. So to calculate that, you have a really handy node called orient along curve. So let's use this, which should create for each point a normal vector as well as a up vector, which can be used to orient each point on top of the curve. Right. Now after doing that, I'm going to create a for each loop with the for each number option. Now the number of loop corresponds to the number of segmented curve, so which you can get it from this pairs detail attribute, which is this pair count. So this pair count is actually the number of segmented curve. So let's access to this detail attribute from this for each end at this iterations. Detail pairs what was the name? Forgot the name. Pair count. Pair count 0. So you have 15 iterations here. Now next thing you want to do is to access to this pairs array at each iteration and use those first value of the vector 2 and the second value of the vector 2 to trim this curve to create each segment. To do that, I'm going to use a carve node. Using carve node, you can trim out the curve using the first u and the second u, like here, and the parameter. By changing this value, you can trim out the curve based on its u value. So by accessing to the u value, the pair of u values stored in pairs, I can create each segment of the curve inside the loop using the iteration value. So let's test it out using the single pass starting from 0. So for the first pass, I should be able to get this 0 as the first u value and the 0.10003 as the second u value. Okay, in order to access that, I also need to use the detail attribute called iterations from this for each count. Now let's do that by creating a detail expression for each of the parameter, first u and for second u. Okay, let's start from first u. First of all, I'm going to access the pairs. The name of the attribute is called pairs, and in order to access the vector2 float vector2 arrays, I need to consider as a one single array for this one. So if even though you have a nested array looking like a nested array, you actually, in order to access from the expression, you need to count this as a one single array which starts from 0, 1, 2, 3, 4, 5, 6 and so on. So for the third value, I need to say if the iteration is 0, then I have to multiply it by 2, and for the second u, I have to multiply the iteration number by 2 and add it by 1. So this should be this value should always be the even number, and this value should always be the odd number. I guess I'm missing some value. I guess I'm missing some stuff here. Maybe I have to do it like this. Still not working. Okay, so I am accessing to the pairs, and that the name of the attribute is called pairs. Yeah. And this is the number of index. What if I change this to 0 and 1? Would it work? Doesn't seem to work. Now let's see the errors. Unable to evaluate expression. Okay, something. Okay, I didn't need the semicolons here. Right. So if the iteration is 0, then 0 multiplied by 2. This still works. If the iteration is 0, 0 multiplied by 2, added by 1. Okay, so I need to replace this 0 with the iteration value retrieved from this for each count. So let's replace this with another detail expression accessing for each count iteration 0. And also replace this. Okay, now let's check if this still works. Now, so this should be the first segment. If you check the first u value and the second u value, you have 0 and 0.10003, which if you look at the detail attribute of the pairs, then you have this first u value and second u value, which seems to be correct. So let's go to the second pass. If I set it to 1, Now the curve have just disappeared. Let's see why that is. Going back to the pairs, and if you look at the value, the second pair of the u value is pretty much close to each other. So I guess that's why you didn't actually see the curve, the intersected curve here. So let's skip this one to see the third u pairs, which seems to have some differences between the first one and second one. So the third one should have some curve, and yeah, it seems to have. And if you look at the first u and second u, the value has been successfully retrieved from the detail. So I guess it's working. Okay, now if I turn off this single pass, everything seems to, every curve has successfully segmented, I guess. Maybe you can check it by changing the slider value here. Yeah. Alright, now the next thing I would like to do is for each segmented curve, maybe I should test it with the single pass 0. For each segmented pass, I want to resample this curve with some threshold where you want to set the base of the bone, then create a arc-like curve as a bone on top of each point on the curve, each point on the resampled curve. And you also want to avoid creating a bone on the end point, the first point and at the end point, so that because those end point of the segment is the intersected point, intersected with another curve. So you want to avoid creating the bone so that you don't have a collision between two bones. Alright, so let's do that by first creating a resample. And if you show up the number of points here, what you want to do is control this length in order to resample this curve, and you might want to set the tree polygon as subdivision to make it a bit smoother. Right, so let's parameterize this length as a parameter inside this new node, so that you can control the resolution of the bone array. Maybe I will create a separator in between those Lissajous and the bone-based parameters. Let's name this, how should I name this? Gonna name this bone div, and the range between 0 to 2. Okay, and go back and create some value here, copy this parameter and go back to the resample. Let's copy this here by paste relative references. Right. After doing this, I'm going to create a bone-like curve on top of each point using an information that I've retrieved using this orient along curve. And also you might want to animate this bone rotating using this curve and an axis. So I'll do all of those using one single point wrangle node. Right. I'm gonna name this bone. So this one, it's going to be a bit long, guess, or a bit complex in order to write as a script. First of all, I need some parameters that I want to control. I want to be able to control. First of all, let's create a number of twisting, or number of twisting using this axis, how much it should twist, as an integer, so that the integer will be used multiplying with a 2π, so that the twisting will be looped within this whole curve. So how do I name this? Twist num. Let's also create the parameter in order to determine the length of the bone. I'm just gonna name this bone length as a float. Okay, another parameter that I would like to use is to control the angle of this bone. So whether you want to make it straight or make it curved like an arc, maybe I would want to have some parameter to control that. So for that, I'm going to name it as bone angle. Okay, finally, in order to create a bone curve, you need to have multiple number of points. So let's create a parameter to control the number of points. I'm gonna name this bone res, stand as a bone resolution as an integer. Okay. And finally, maybe I would like to have a parameter to create an animation, so I'm gonna name this as a time. Okay. Now let's have all those parameters promoted inside this node controller again, so that I can control it later on using this controller node. Right, to make it easy, I'm just gonna drag and drop the parameters like I did before. So first of all, bone length, bone angle, time, twist num, bone resolution. Maybe I'm gonna bring this twist num to above. Right, let's also set some ranges for the twist num from 0 to, maybe set it to 20. Bone length, I'm gonna set the maximum to 4. For the bone angle, I'm going to set it the maximum to 2. And for the bone resolution, the maximum I'm gonna set it to, say, 30. For the time, let's just keep it as it is from 0 to 1. Alright, accept. Now let's change those parameters that I have set randomly for now, like this. Right. Okay, let's go back to the bone and let's write some code in order to create a bone-like structure curve. All right. First of all, I want to ignore the first point and the end point. So let's make a condition. If the pt num is not equal to 0, and if pt num is not equal to endpoints (0, -1), then first of all retrieve the up vector from the point. Okay, now first thing I would like to do, I guess let's use this twist num value in order to have the base orientation of the bone. To do that, let me just create a straight line using this up vector. So in order to create a straight line, I also have a number of points in order to create the bones here. So let's first create a for loop from 0 to bone res. Create a position for each bone position, which should start from current point, position plus a up vector multiplied by this bone length as a maximum value, and for each loop, so I want to use this bone length when the n is equal to bone res -1. So let's create a threshold value called nt, which is from 0 to 1 within this loop. You can calculate that by dividing n with a length bone res -1.0. So I'm going to use this threshold multiplied by this bone length for the pause position. So if nt is equal to 1, you get the final point position like this. If the nt is equal to 0, then the position will be at p. Alright, now let's create a point using this position. Now let's check this out. Now I am seeing some list of points here. Now let's also create a polyline using those points that I have created. So just before getting into the for loop, I'm going to create a curve called arc, or should I say just polyline, using add prim as a polyline. And the first I think this is good. And then let's use add vertex to add the newly created point inside this polyline, so within the loop, which should create a line on top of the curve like this using the up vector. Okay, that looks good. The length seems a bit too long, so let's reduce the length, something like this. Also maybe reduce the number of bone resolution to something like 5 or 6. Okay, that looks good. Now what I want to do next is to twist this direction of the bone using this twist num parameter. Okay, to do that I'm going to create a rotational matrix. Alright, so first of all, create a ident matrix. Then let's rotate this matrix using an angle based on this twist num. So twist num multiplied by pi by 2 multiplied by 2, so that you could have a looped rotational twist. And you also want to multiply this by a value t, which you have in each point attribute, which determines the initial u value of the curve itself, the whole curve, independent from the segment. Right, let's check this out. And in order to create a rotation, you also need to have a rotational axis. For the rotational axis, I'm going to use the n. Okay, now that I have the rotational matrix, I need to use this somewhere in order to rotate this line. So the position that I could do that is somewhere around here, which is this one. So I can rotate this up vector by this matrix in order to create a rotational twisted bone curve. So let's multiply this up by matrix right after the up, like this, and that seems to work. And let's exit this for loop to see if the whole curve has been twisted correctly, and there seems to be no glitches, no sudden jump for the twisting. And if I change the number of twist, still seems to create a smooth twisting, so that seems to be good. And you can see that at the intersection point you don't see any bone structures created. That is also working as intended. Looks good, looks good. Okay, now let's go back inside a for each loop. Let's check this single pass again. Let me save this file first so that I won't lose what I've wrote here. Okay. Now next thing I would like to do is to create a arc-like curve instead of just lines by using a parameter that I have set, like bone angle. Okay, so to do that I need to have one more rotational matrix, and in this case inside this for loop when we were creating this point. using this bone resolution. So right after getting inside the for loop, I'm going to create another matrix, rotation matrix called mat2, starting from ident, and let's create a rotational angle for each point. I guess I could use this NT threshold value for the rotational matrix. So let's rotate this mat2. Now the angle that I'm going to use here, to calculate here, is, let's start with this one. So I want to use this one as the final rotated angle for each point, for the point. So when the NT is equal to 1, I want to use this bone angle as it is. If the NT is equal to 0, then I want to multiply 0 with bone angle. So bone angle multiplied by NT, and I guess multiplied by pi as an angle. So if the NT is equal to 1, then this value will be 180 degrees, and if you set the bone angle parameter as 1, then you get 180 degrees angle. If you set it to 2, then you have 360 degree angle. Okay, and the axis is again n. Alright, now that I have the second matrix, second rotational matrix, I can apply this at the same position here, same up vector here. So I'm just gonna multiply mat2 at the end, and now I seem to have some arc-like curve based on the parameter that I have set, which is this one. So if this is equal to 1, then the angle becomes 180 degrees. If it's 0, then it becomes more straight. Now I can also increase the number of bone reds in order to make this rotated curve smoother. So if I set it to something like 20, it becomes more smooth like this. And if you have more twistness, you have two different angle rotation applied. First a twist, and then the straightness of the bone. Yep, seemed to work. Now finally, I would like to be able to control the twistness as an animation later on. So to do that, I'm going to modify this first rotational matrix a bit using this time value. What I'm going to do, I'm just going to add a shift angle, which derives by adding a pi multiplied by 2 multiplied by time, so that if the time is equal to 0 and 1, you get the same value. Okay, let's see. Now I can see that the rotational animation seemed to work. So if I use if I use a global expression like frame, then I could animate this value. Okay, seems to work well. Okay, one final touch. touch, what I want to do is to apply a p-scale attribute to each of the point so that I could use it later on to determine the thickness of the curve at each point. So I'm going to create a point attribute after I have created point named as p-scale at p, and I'm just gonna calculate the value as 1 minus npt, so that if it's close to the base of the curve, if the point is close to the base of the curve, then you have 1. If it's close to the tip of the curve, then you have value 0 as a p-scale. Right, now you also want to set the p-scale for original point number, point value, and maybe by 1. Maybe I could do it here. Okay, seem to have an error here. Let's see where that is. Okay, this one. This should be NT. Okay, now if I look at the geometry spreadsheet at point, I have p-scale. Okay, looks good. I think it seems to be okay. Now this is everything you should do inside a for loop. So let's check off this single pass, and you have this something like this. Now let's also check the animation by setting some global expression for the time parameter here. Something like ff divided by fn. So based on the starting value and the end value, you always get a value from 0 to 1 based on the timeline position. So let's set it to something like 60. If I play it, yeah, the animation seems to work well. Yeah, this itself is pretty interesting. You could also end this and tutorial right here if you find this good enough. Okay, that looks interesting. Right. Okay. Now what I'm going to do next is to thicken those lines to create more like a geometrical sculpture. To do that, I'm going to use my favorite node, polywire, which I use a lot of time, which I use a lot. Okay. Now before doing that, I'm going to fuse to remove the duplicate points, and in order to calculate the thickness, in order to set the thickness of the curve, I want to use the value p-scale at each point. So I'm going to create a expression here using the point. OP input PT name p-scale 0. Okay, do I have some errors here? Looks like so. Okay, I need to close this. Okay, I also need to set the maximum thickness using with the p scale, so let's have another parameter here. I'm gonna separate this again and then create a thickness parameter, which could be from 0 to 0.1 or something, maybe 0.5 or something. And let's copy this and paste it here, multiplying this p scale with the parameter that you have just created. Okay, now we seem to see some interesting shape here. If I change the thickness, yeah, and let's normalize this to fix the normal value. Yeah, this seems to work. I'm gonna set the division to 4 as it is, but you can also control this if you want to have more smooth sections, but I'm gonna set it to 4 for myself. Right, now finally I also want to set the colors for this geometry based on the p scale, I guess, which could be useful. So I'm going to set the color here, set the ram from attribute, access to p scale, and so this seems to be the corresponds to the tip of the curve. This seems to correspond to the base curve, which is the Lissajous curve. So I'm gonna set it to some darker colors like black. This one to be more white. And for the middle color, I'm gonna set it to red. And let's see how it looks. Yeah, I guess I would like to change the base color to something more, yeah, something like this. Like this thing. Okay, let's hide out the edges. Okay. Now let's also increase the thickness. And I think we have, this is it. This is the final look of the sketch. If you play the animation, you see that the bone structure is rotating based on the research curve. And what you can do, you can increase or decrease the bone's resolution. Well, first of all, the research curve parameter itself. You can also change the density of the bone, which makes it slow if the density is really high. Number of twists. Length of the bone. Bone angle. Resolution to make it smooth. And so on. Right, so this is it. A rather simple geometry which I have created from the Lissajous curve. Doesn't really have to be from the Lissajous curve, it could be from any kind of curve. I guess the point here today that I wanted to show is how you could separate the curve using the self-intersection point. I guess the method that I showed you today could be used in other purposes for geometrical analysis. So if you find that interesting, I'll be really happy. Okay, that's it. That's it for today. Thank you very much, and hope to see you again.